Yeah, thanks for the invitation. It's nice to be here. Thanks for those of you who weathered I don't know if the roads are bad. I mean, that's not what I meant about it. It's a small audience. It's the last day. That would have been the same regardless. But just if you risked your life to get here, thank you. Yeah, so in fact, I would generally say I don't know what people's background is, but maybe that's a lie because there's so few people I could figure it out. Yeah, so the talk will be fairly elementary. You can so please feel free to interrupt, ask questions at any point. And then of course at some point it will become non-elementary, and then I will forgive everyone, and you'll forgive me if you don't follow every detail. Okay, so yeah, I guess if we were, I did imagine if like alien anthropologists were studying humans giving talks. Like in class, the first day the question would be sort of, what does every good talk have to have? Because, and the students would say, you know, every good talk has to have a joke and a proof. And then the teacher would say, no, that's very naive. Every good talk has to have a neurotic meta conversation at the beginning about whether or not it will have a joke or a proof. I don't know if that qualified. It was a meta conversation. But okay, let me start with a very basic setup that doesn't require any background, and then I'll tell you some applications of it. So suppose you have a convex body K in Rn, and you have a point in this body, and then you will want to move around this body, so there should be something that's encouraging you to move around. So let's also suppose that on the body there is a vector field, say a time-varying vector field. So some function that maps points in the body to two vectors in Rn, actually two tangent vectors, but
nowhere zero?
No, I don't put any constraints there on the vector field. I mean, if it's, it's true if it's zero somewhere, you're not going to be moving very much. But I mean that will be fine. In fact, I mean, for instance, yeah, I mean, if your vector field was the gradient of a convex function, then it would be nice for it to be zero at the optimum, and then you can, I mean, it will be, and then you can stop moving around. Of course, that's not exactly true. So that's a lie. That's so no, it can be zero, because obviously the gradient will, you will be at the optimal point, but the gradient will be pointing, say, outside the body. No, in the vector field, I mean, in general, at the end of the day, we will want it to be continuous, and maybe for some stronger things, Lipschitz continuous in both K and the time parameter. But in general, you can just think about this setup. So if you want to flow in this body along this vector field, okay, what does it look like? Something like that. Then these are the natural dynamics. The derivative of your position at time t is the vector field at your position. Right, you can think about this differential equation. It's great. There's no problem until you get to the boundary, of course. And now you can even now the vector field might point outside the boundary, but I want you to of K might point outside of K, but I want you to stay inside. So you need to do something at the boundary, otherwise, to make this evolution make sense. So there's a very natural thing to do, which is just this is an interesting thing, by the way. So PowerPoint does this automatically. Like, it automatically morphs between these two things. But you can see there is some strange matching algorithm going on, because it didn't identify every vector here with its...
How does it do it automatically?
I think probably it computes some hash of every object and then computes... But it doesn't seem that it is, because it's not... there is something... I mean, you see...
You didn't plan for that first?
No. So I assume that what happens actually is it computes some kind of hash of every object, and then it tries to do some matching between them, and then just for every object computes a continuous path. But that's a mystery, that some of the vectors changed identity. Maybe it's related to Shmuel's talk from yesterday, right? I don't know if that's some... If you go around, I guess, no, it will be different. Okay, so wait, what happened? We're missing something? Yes, so, okay. That's quite strange. All right. So, so I will skip. So ignore everything on the slide for one moment. There's an intermediate slide which contains this picture. There is a very natural thing to do, which is just when you step outside the body, project back into it. Once you decide to do that, but yeah, so I mean, you can infinitesimally define this very easily. Except that when you do it, you'll see that, I mean, that right, like if you want to project back into the body, there is some degree of freedom there. Which inner product do you use? So you can actually, I mean, you can use any inner product you want. You could use so any Riemannian metric on K will give you some algorithm for projecting back into the body. That's fine. But if you want some algorithm that has some kind of global characteristic, so for instance, if you are flowing along the vector field of some convex function, you can imagine that you want some control on how fast you converge to the minimum, then an arbitrary Riemannian metric, may not have this property, but there is a well-studied class of metrics that do have this kind of global control. And these are the metrics coming from the Hessians of convex functions. So it's from strongly convex functions. Yes.
I'm not sure I understand the framework.
Mm-hmm.
I mean, you are talking now about an algorithm when you know the boundaries of the convex body,
Yeah.
and you try to find. It's not like you want to understand the convex body.
In general, the setup is I have a convex body and I have a vector field. So somebody's telling me try to move, and what can I do? So there's various.
You want to try to move to a minimal point of some function.
It's a hard. I want to move in the direction of the vector field. So if the vector field is the gradient, say, of a function, then I am trying to minimize the function. Say it again.
This is motivated by interior point method.
So okay, give me 1 second. There will be the the three origins of these in a second. So the class of Riemannian metrics that we'll think about are the ones coming from the Hessians of strongly convex functions. So here's the local inner product at X. And I'll tell you why these are interesting in a second. There is some sense in which, at least if you're working on all of Rn, then these are the only ones that have this kind of global Lyapunov functional associated to them. No. I mean, okay, sorry. I'm being a little bit. Let's suppose that K is compact and convex, right? That's all. So given that, I don't need. There's no problem. So for instance, I mean, if I do the Euclidean projection, I'm just looking at the minimum of the point at minimum distance from where I am, and this is unique. This is where strong convexity comes in. Strong convexity says that the projection is unique. I mean, combined with convexity of this of K. So this is like some continuous time algorithm. Depending on how you discretize it, you will get lots of known algorithms. So mirror descent. This describes basically exactly interior point methods. Again, when there are non-trivial issues in discretizing these things, and then you have to make decisions based on lots of other factors. And also, I mean, there is the field information geometry studied by the Japanese for a very long time, and then this is a sort of, okay, they study flows exactly of this form for these Hessian structures. And you can describe so the slides are, so one can describe the dynamics of this algorithm in the following way. What happens? So so basically the Hessian times the derivative has the following form. This thing you expect. This says you're moving in the direction of the vector field, but then of course you need some normal forces from the boundary to keep you inside. I mean, if you just move in an unconstrained way, you will possibly leave the body. So the claim is that this lifted derivative. One way to think about this is that the tangent space on Rn is not the right place to think about this derivative. So think about it in the right tangent space. So then there are some forces coming from the normal directions. So lambda t lies in the normal cone, which is the set of vectors at X that are pointing outside of the body. Right? So I mean, this is a very natural setup. I will say that like this, I mean, essentially these things are studied in projected dynamical systems and this field called differential inclusions very intensively. this particular setup comes from a paper with Seb Bubek, Michael Cohen, Ian Todd Lee, and Alexander Madry. And so I didn't say the theorem here, but the dynamics here are such that if things are suitably locally Lipschitz continuous, then there always exists a solution, and under a slightly stronger assumption, then it's in fact unique. So under fairly general assumptions, there's a sort of unique trajectory corresponding to this algorithm. And and the reason we consider this special kind of structure is that there is a class of Lyapunov functions associated with dynamics that say that in some sense you're always making progress. Okay, so this is the Bregman divergence associated to the function phi, and here's a general fact, which is quite easy to prove just using the chain rule, given the definitions. It's that so think about it in the following way. Here's a point y, here's a point x. Suppose that, and here's the vector field at x. If there's a positive inner product between these two vectors, then in the unconstrained setting, if you move along this direction a little bit, you will get closer to y, say in the Euclidean distance, right? You're moving along some direction that's correlated with y. Now, when you add in this projection, it's not necessarily clear that you're, and in fact, you can compute just by Pythagoras the amount of progress you're making. If you now project back into the body, though, it's not clear that you'll be making progress towards y, right? Like the projection could destroy, depending on how it's defined, it could destroy the progress. And this fact here says that it's not the case. So you get, well, it's not the case if you consider the progress in the correct measure. So if you consider progress in this Bregman divergence, then you get, like this divergence is decreasing exactly as you would expect the squared Euclidean distance to decrease in the unconstrained setting. Also in the constrained setting if you do Euclidean projections. But is it clear what this fact is saying? Okay, good. So that's, now I'm going to give you some applications of this. Okay, so this is the basic setup. So if you have any questions, you should ask about them now. I will tell you some situations where you can apply these things, and you might be surprised, maybe not. Okay, so for instance, so here is a theorem that everyone knows, say Ross theorem for three-term progressions, but I'm stating here the best quantitative estimate due to Thomas Bloom. If you take a subset of 1 to n that contains no non-trivial three-term progressions, then then the set sort of it's classical that the set has to have a size which is little o of n, and in fact you can get some concrete estimate there. And as everybody probably knows, there is a conjecture of Erdős, which is co-credited to Turan by Erdős, I think, which is that not just in the three-term case, but the three-term case is still open, that you should be able to get this to be going sort of that the size is if there are no three-term progressions, something n divided by something growing faster than log n. Basically, you can think one way of proving, for instance, that the primes contain non-trivial three-term progressions is just to say that every subset with the density of the primes contains three-term progressions. That would be the easiest way. The prime number theorem tells you the density of the primes is like 1 over log n. So you could hope to that just by density arguments you find three-term progressions. Okay, so this is a theorem. So you can prove it using this setup. Okay, so. What are the underlying things? Now K is just a simplex over, so G here is say a finite abelian group. K is the set of probability measures on G. The strongly convex functional is the entropy, and then the set of directions that one considers is the set of characters in the dual group. So this, of course, it doesn't necessarily make much sense. It's just a claim that one can prove this using these methods, and the proof is quite a bit simpler than Bloom's proof. In particular, here there's lots of additive combinatorics, and here there's only what I told you. So you have entropy and this algorithm and this control. So how can you think about this? So one of the applications for this setup comes in learning theory. And then what you do is you think about it as sort of y as perhaps some unknown quantity that you're learning about, and xt is sort of where you are at the current point in time. And now when this vector field comes, you learn the vector field at your point. It's giving you some information about y. And then when you sort of update according to these dynamics, if you think about the divergence as being a measure of information, how much information does x have about y, then it says that when you update according to these dynamics, if this is really information about y, in the sense that y is more correlated with the field than x is, then you're learning quantitatively something. So, okay. So at a high level, one way you can think about this is that you have a probability measure, which is just the uniform distribution on a dense subset of 1 to n. And now you want to approximate this by some simpler measure, such that the approximator has about the same number of 3-term progressions as the original. That's, you could think about this. Now the approximator is distribution, so you have to write down, to count 3-term progressions, you need to write down a sum over x, y, z, f of x, f of y, f of z, such that blah, blah, blah. But so you can imagine the following. You want to approximate this, the uniform distribution on this set by some other distribution, such that counting 3-term progressions in one will tell you about 3-term progressions in the other. So there's some family of tests that don't distinguish between the two, and if those tests don't distinguish, then also the number of 3-term progressions is about the same. And so now you can imagine trying to construct such an approximation. You start with the uniform probability measure, and then every time there is some test on which you're differing from the on which you're differing from the set, you try to improve your approximation along that test, and then that's sort of the vector that comes in the vector field here. And the fact that the approximation that you get is simple corresponds to the fact that if you started with some object that had very high entropy, so like the density is saying that, for instance, a set of constant density on 1 to n has all but a constant number of bits of entropy. It's the uniform distribution. I mean, if I select a random point there, the amount of entropy I need to specify it is very close to the maximal amount. So you want to say that if you start with such a distribution, if you start at the uniform distribution, then this converges to the unknown thing that you're approximating very fast. And if it converges fast, then what you will get will be simple enough that by hand you can say something about the arithmetic structure.
I do understand. You start from the uniform. K is just the simplex over 1 to n.
Mm-hmm.
And you start from the uniform distribution.
Yeah.
And you follow this dynamic.
Yes.
So eventually,
There is somebody. I mean, there is another aspect here, which is what is the vector field. The vector field is something that you are choosing at every step.
Where is A?
What is A?
A is the input to this theorem.
Oh yeah. No. So so this is how you choose your vector field at every step. Basically you can think about it as I have a class of tests that, and if there's some, I take some test which is distinguishing A from my current approximation. Now I want to move in the now it makes sense. Okay, move in the direction of this test.
So you're saying that for every point, what are the points? They are distributions.
The points are the f's. They're the distributions.
So I have a point, and now
Yeah.
you need to tell me what is ft at that point.
Yes.
And so you look at A and you see which test is the most valuable.
I will find some Fourier coefficient on which f and 1a divided by the size of a differ, and that will be and I will move in that direction until the test becomes very close to satisfied. And as long as the test is far from satisfied, I'll be making a lot of progress in this Lyapunov functional. And therefore, I can't, and basically what the approximator I build, for instance, in the most basic set of the approximator I build will be a junta, because, it will not be a junta, that's a lie, so ignore that. It will be some, what are they called, parity decision tree. It will be some function of a small number of characters, because I can only visit a few characters before the Lyapunov potential says I exhausted all of the uncertainty about the set A.
It's because you're converging fast.
Because the relative entropy between my current measure and so the relative entropy between A and my current measure is going down every time I move. So I can't move too many times, and every time I move, I make significant progress because otherwise the test wasn't violated very much, and then I was happy anyway.
And then what is the punchline? You reach someplace,
Yeah, that place now, by definition, cannot be distinguished from 1A by your family of tests. And now there is some additional work that you want to say that that fact implies that your approximator has lots of progressions.
So it's
And the tests are chosen such that if the tests don't distinguish between the characteristic function of A and the approximator, then your three-term progression count will be the same, approximately the same.
So the statement would be that for every such an A, there is a distribution on 1 to n, which somehow, for simple reasons, must have. This I don't understand. So
Yeah.
you start. There are two players here, which I don't understand how they interact. You start with uniform distribution. There is an A which somehow determines the field that governs your work, right? And so you follow this dynamics, you use your theorem, and eventually you reach another distribution.
Yes, which I think about as an approximation to the characteristic function of A,
Okay.
but not an approximation in some, like an LP norm approximation with respect to the family of tests. So
And then, because it's simple enough, you can prove by hand that this is a contradiction. That's
you can prove by hand that this is simple. It has a lot of entropy, and therefore it has to have lots of three-term progressions in the generalized sense.
Sparsity of A in this argument?
No, the density of A is coming into the entropy of the initial distribution. So basically, at every point, every time you make progress, you're learning about A. So if A doesn't have very much uncertainty in it, you cannot learn too much about it, and so you have to stop after a small number of steps. This is not okay. So at least when you use the entropy, I mean, you can state it not in this framework, and I don't think. Okay, so maybe this seems a bit surprising at first, but for instance, if I tell you to think about, especially the weak similarity, the weak regularity lemma in this setup, then it's somehow the proof. I mean, the proof of the weak regularity lemma is just your regularizer is the Euclidean distance. Your test functions are cuts, and every time there's a cut on which you differ from the thing you're trying to approximate, you refine your sort of your approximator in the direction of this cut, and then after some small number of steps, you have to stop. Also, the strong regularity lemma you can state in this setup, where now the directions are given by sort of partition refinement at every step. This is not so interesting for the strong regularity lemma simply because the running time is not so important, because what you get is a tower in the running time. So I guess that makes it really important, but in some sense not important. Okay, that's one application. Let me tell you, I'm glad we had this discussion because there's nothing that makes sense on this slide, and I'm going to continue that theme. That's great. It makes it easy to design slides. You just put some hint about what should happen, and then the audience can interrogate the rest. Okay, so here is a problem which came up in computer science. It's very natural. There's some families of polytopes that we care about, like associated to NP complete problems, like TSP, or the cut polytope, which is the problem underlying the max cut optimization problem. And one way that you can optimize over you can have some complicated convex body. This is not one. This is just a square, but which is hard to optimize over. But if you could think about this body as the shadow of a simpler body, then it turns out that by optimizing upstairs, because the body upstairs is simpler in some way, you can also optimize downstairs. So for instance, if P is not equal to NP, then it should be the case that the cut polytope or any polytope associated to a NP complete problem should not have very simple lifts. So convex bodies in some higher number dimensions that are simple enough that you can optimize over them and project downstairs to the body you care about. So the lifts corresponding to semi-definite programs are called Spectrahedra. These are just the intersection of the positive semi-definite cone with an affine subspace. And okay, so with David Storr and Prasad Raghavendra, we proved that in fact the lifts, if you have the cut polytope on an n-vertex graph, then you need dimension of the lift has to be at least some constant to n to some power. So in computer science language, exponential in the number of vertices. So this is okay. You will not prove p equals np by giving an STP characterization of the cut polytope, and the way we do it is to start with the supposed lift, and then apply this procedure to approximate it by simpler things. And there, the underlying convex body. Okay, so this is a strange thing. This is a function from the discrete cube to positive semi-definite matrices to R by R PSD matrices. But if you want, this is a quantum classical state. That's what this D is. There's a classical part, which is n bits, and then there's some quantum part, which is R qubits. So these are density matrices. This convex body K. The strongly convex function you use is it's the von Neumann entropy. Again, this is a mixed classical quantum entropy. That's why there's an expectation over X there. And then the set of directions is the set of low degree squares. So this P of X is a matrix where the entries of the matrix are low degree functions of X, and that square is the matrix square. So I'm definitely not going to say much here, but if you do a similar kind of setup, then what happens is the fact that if you assume that the lift had small dimension, it corresponds to the associated D having a very large, nearly maximal von Neumann entropy. And therefore, again, these dynamics run in a small number of steps. And what you construct is something, some simple function of low degree squares, which itself yes. You walk on the set of density. You run this algorithm on the convex body of density matrices. The directions are coming from low degree things. And so at the end of the day, actually you construct something which is close to a low degree square, which means that with respect to low degree square tests, you approximate your spectrahedron by a sum of squares, spectrahedron, whatever it means. And now you can use explicit lower bounds for sums of squares relaxations of those polytopes that are not easy but are known. Okay, so that's another setup.
Then you prove with that you prove what?
Yeah, with that. So the point is, any small dimensional lift is approximated by a sum of squares lift, which means that it cannot project even approximately. It cannot project to the body downstairs because low degree sums of squares lifts cannot capture NP-complete problems. So at the end of the day, you prove a lower bound that there cannot be a small dimensional lift. And again, the small dimension comes in here essentially only through the assumption of the associated object has extremely high entropy, and therefore this process will converge fast.
So what seems to be common to both these proofs that you just sketched is that you have this dynamics, and eventually you run into a spot that is too low in entropy, and then you should be able by hand or by using something like this sum of squares argument show a contradiction there. So
you're constructing simple approximators. You can think about this as independent of the contradiction you want to show. You have something, you construct some. The only reason the contradiction comes up is because the family of tests have to be rich enough that they can transfer the contradiction from the approximator to the original object. But then it's just I want to approximate an object with respect to this family of tests. And so if the object itself doesn't have very much uncertainty because it's close to maximal entropy, then you cannot take arbitrary tests. Obviously, if the test looks very closely at the probability space at what's going on at a single point, then you will not be by making progress with respect to this test, you will not actually be changing things very much. But if the tests are sufficiently smooth, then you can say that this convergence will be. The thing you didn't see about smoothness is that sort of you care about how much if you're violating a test by epsilon, then obviously, for instance, like the L infinity norm of the test matters because if your error is epsilon, really that should scale with the L infinity norm of the test. So some notion of smoothness of the tests matters, but and so for instance for this problem before we thought about it in this framework, we had no idea what to do. Like this is not an example like where like on the previous slide you could. It wasn't done, but you could think about this. If you look at this sort of structure and randomness area, they're having some. Look at the Samaretti's proof of the regularity lemma. Having some energy functional that improves at every step. That's very natural. That's what happens. So this is a.
Can you capture the original proof? The original proof of Samaretti is really very simple and just can it be viewed in this framework that you're describing here?
I'm 95% sure the answer is yes. It's only a bit of apathy why that I don't know that the answer is 100%. I can say that I asked Luca Trevisan, should this work? And Luca said, yeah.
Source for the 95%.
Did you ask about P versus N?
I mean, I wasn't trying to trick him. I mean, if you don't know Luca, the point is that Luca has no problem to say nothing. So, I mean, yeah.
Do you want me to slow you down?
Go ahead.
So you said the previous slide with the Roth theorem, you could potentially think of coming up with the proof without using this proof. Can you explain again why here you had no idea what to do, and when you look at it this way?
Because the natural thing to do is you take this. Getting a low degree approximation is very natural. In fact, there's a classical setup with linear programs where you want an approximation by juntas, and it's very natural to just try and construct it by hand. And for juntas, you can, because juntas are, if you have a probability distribution and you want to say that it somehow depends only locally on the inputs, distribution on the cube that depends only locally on the coordinates, by hand you can sort of see what are the influential coordinates, okay, take those out, keep going. The structure of low degree squares of polynomials and PSD matrices is sufficiently complex that trying to understand it by hand was just unsuccessful. And
So instead you find some kind of thing you want to optimize, then you just run something.
so if I'm allowed to be philosophical for 1 second, it's really the case that once something is so complicated that it's better to just treat it as something that's unknown. So it's like that's why maybe sort of the analogies to learning theory are relevant, even though there's no uncertainty in the setup because you know everything. Which is just that like trying to interact with this complicated object on its own terms is very hard. So you only interact with it through some small views of it, some limited views. And then it's nice because if you only interact with something through limited views and you don't interact very long, then you yourself can just not be that very complicated because you're some accumulation of a small number of limited views of some object. Okay. Again, that's not like that's if you state the regularity lemma, that's exactly what it looks like. I mean, you have every object has a very simple approximation as long as you're willing to give up enough in the tests, and you need the object to be dense, which corresponds to the entropy assumption. Oh, okay. So of relevance to this conference, for instance, is the construction of Batson, Spillman, and Srivastava for sparsifiers of graphs. So what do they prove? If you have a graph, any graph, then you can take a subset of the edges, put some weights on them, such that the resulting weighted graph approximates the original graph in terms of every test vector is approximated up to 1 plus minus epsilon. And the size of the approximated number of edges, the support of the weight function is n over epsilon squared. So in particular, if you apply this to the complete graph, yes?
You said to get them slowly.
No, because you know the statement. No, but okay. Yes, you take any graph. Now, there exists a subset of the edges. So for every epsilon, there exists a subset of the edges of size n over epsilon squared, and some weights on those edges, so that the quadratic form corresponding to the Plossian of this weighted graph is an approximation to the quadratic form of the graph up to epsilon.
Did you say that the spectrum is well approximated to the spectrum of the original graph, right?
Every test vector has up to multiplicative 1 plus or minus epsilon. The same the quadratic form on every test vector is the same.
But let me ask you now, instead of asking you at the very end, do you have a suggestion for such a definition, why they mention and the statistical complexes?
The specification.
I mean,
You need it for every Laplacian, for every dimension.
right. I mean, the answer is I have no idea, but I thought I'll plant the idea and then I'm a little sleepy, so then I'll just go to bed and you and somebody. But you can think about the proof of Batson, Spillman, and Srivastava as sitting exactly in this setup. So this is not my observation. This comes from a paper of Alan Zhu, Lau, and Orecchia, where their convex body is now again the set of trace 1 positive semi-definite matrices. Your regularizer is now, so if you use the entropy, if you use the von Neumann entropy trace x log x, then you will get sparsifiers with n log n edges. And in fact, if you think about what I said appropriately. So the dynamics, when these dynamics are on the simplex, you can often think about, then you're moving in probability distributions. You can often use so you can think about, okay, I shouldn't say it, like stochastic calculus. You can think about the update to this distribution as being given by some random process. So if you think about doing that here, like stochastic gradient descent, instead of moving in the gradient direction, you sample somehow from the gradient, and then you just move in this direction. So if you do this with the x log x regularizer, and you do this stochastic gradient descent, then you will reproduce our algorithm and analysis of Spielman and Srivastava, which is that if you sample the edges of a graph according to their effective resistances, you will get a good sparsifier. The same thing we said before, order n log n over epsilon squared edges. If you want to do better, you need to switch the regularizer, minus trace squared of x, and then the set of directions here is the obvious set of directions, which is that you move in the, okay, it's not clear what xe is, but these are the single Laplacians corresponding to edges. These are the edge Laplacians, so you're moving in the direction of edges of the graph. So again, if you move in the direction of a small number of edges, you will get a sparse approximation. Yes. By the way, it's not quite true. Really, you need to first turn your graph, the Laplacian of your graph, into the identity matrix so really, these xe's are the edge Laplacians in the basis where you change by the inverse, L to the minus 1/2 on both sides. But okay. Yes.
I don't know. It's a very. Okay, I'll ask it.
So if you've looked at that paper, there are these magical like barrier functions and so on that come up there, and then you can wonder where they're coming from.
Like this phi, for example.
Oh, the phi is yeah, that's from God.
It's from God.
Yeah, but it's no, but the potential, the way that you analyze how well you're doing, so that you don't go for too many steps. Once you have the phi, this part comes out
So the
for free.
Why are you saying
Yeah.
wait,
replaced by that.
No, the barrier function is just the analysis is not so different. It's a bit simpler when you think about it in the setup, but the barrier functions, you get the same. But I mean, this Lyapunov functional is very closely related to their barriers.
what is the word barrier here?
Oh, sorry, yeah, it's they have these functionals that control the spectrum in a smooth way on both sides, so that you sort of eventually you're converging. Right? If you state this in the right way, you're just trying to approximate the identity. So you want all the eigenvalues to converge to 1. So
Oh, that's what you meant by multiplying by Laplacian on both sides.
Yeah.
To find the approximation. So I'm just wondering if you do it in higher dimension, this could potentially lead to an algorithm for constructing an expander, because you ask your algorithm to approximate, I don't know, the complete graph.
oh yeah, I mean this is an algorithm which is now once you have there is a paper of Lee and Yintad Lee and He Sun, which shows that you can do this in linear time. For instance, I mean you take this setup and then you put on top of it all the things that those guys can do in convex optimization, and you get some, in fact, very fast algorithm to sparsify any graph. In particular, you can sparsify the complete graph. Yeah, it's a bit okay, right? There's a lie here because it's not bounded degree, right? There is a
Wait, you said n over epsilon squared.
yeah, but it's not bounded degree. That's you could have a
Star also satisfies that.
the
Epsilon squared edges.
Overall.
the degree is not the degree is not bounded,
Fine.
but
I'm
the degree.
happy with that.
Okay, so some people, I can imagine you would also be unhappy with that. Okay, but there are.
But wouldn't that be incredible if you get an algorithm for a higher dimensional expander?
It's not an expander.
Okay, it's not
Yes.
an expander, whatever you want to call it.
Stars.
Okay, one dimension, I guess you wouldn't get an expander.
They have a generalization of this for physically semi-definite matrices in some. I mean, it's not higher dimension, but it's maybe related to that.
I mean, if you take your edges to be, if you write the identity as a sum of instead of rank 1 matrices, higher rank matrices, then things become much more complicated. And the obvious statements of those generalizations are false of sparsification for sort of decompositions into higher rank things. But there are.
There is a paper, I forget the author, but
So in Jerusalem, you always have to fight to speak. It's
Uh, But I
It's left.
yeah, but but that's also the talk is for the audience. I don't mind. I mean, trust me, this is much better than a talk where the audience is like crickets. So, okay, so you can add. So there are some very interesting ways that one might get actually constant degree objects. It's one of the reasons I asked Nadi during his talk about whether there's a Markov chain on the set of things, because now you can think about maybe you want your gradient steps here not to be things that preserve a degree d, so like steps in some Markov chain. Okay, so I will just tell you, and as pointed out, there will not be time to tell you much about it, but I will tell you the problem and the solution. Let me just say that, so there are these problems in online algorithms which have been open for about 30 years, and with Bubek, Cohen, Yintat, Lee, and Alexander Madry, we were able to solve these. I'll tell you the definition in a second. I'll end with the statement of the problem and the solution. But again, with the point is that, again, if the regularizer is simple enough, you can think that maybe you don't need any kind of theory to understand what's going on. But once the problem starts to become complicated enough, like we have no idea how to understand, for instance, by hand the dynamics of this algorithm. And then really it makes the fact that there is this general setup and this Lyapunov function that whatever complicated dynamics are happening is giving you some control of the convergence. That's very powerful. So, okay. So now let me tell you a problem and then we'll stop. Okay. So there is a field called online algorithms, which has the following setup. You have some discrete sequence of inputs to your problem. They arrive online. At every point in time, your algorithm has to take some feasible action based on what it's seen so far. And there's a cost associated with the action. In general, you don't want to pay cost. So you're trying to minimize the cost. And in this field of competitive analysis, you compare your performance against, so how do you measure how well you're doing? You compare yourself against an algorithm that's allowed to see the entire input sequence in advance before deciding on the set of actions it's going to play. Right? So I'll tell you a specific problem in 1 second. But the idea of this model is that you're trying to measure how bad are the effects of not knowing the future on optimization. So if there's an online algorithm which never pays too much more than the best offline algorithm, then you know that you're really doing well, because then you know that the uncertainty is not hurting you that much. Okay, without a specific problem, okay, people don't seem upset. So okay, so here's one of the most well-studied problems. There, it's called the case. It's called the case server problem. So the setup is that let's not go into this. This is a special case of some other problem, which is itself very nice. Okay, here's the setup. You have a metric space, and you have case servers in the metric space. So the case servers are these 3 green points. And then you have requests that come in the metric space. Like here's a request that comes at this point. And you need to move some server to this request to service it. And then, some request comes somewhere else. And okay, so hopefully you're understanding the problem. At every point in time, a request came here, there. I already had a server, didn't have to do anything. A request comes here. I need to move a server, and so on. Okay, that's the problem. I think this stops soon. Okay, so the actions here are which server you move to service the request. The cost is the distance you moved. So your goal is to minimize the total movement that you incur in this process. Okay, so you can so in general, if you move more than, you could move for some reason if you wanted to more than one server at a time. So really the way you measure cost between 2 configurations is the transportation distance in the metric space. This is the Wasserstein 1 distance. That's your cost. You say that your algorithm is alpha competitive if for every sequence of requests, the amount that you pay in movement is at most alpha times what the optimum pays in movement, plus some additive term, which is independent. This additive term is independent of the request sequence. So that's the setup.
But you know the request beforehand, or
No. So that the optimum sees the entire sequence of requests, and then there is some there is some optimal sequence of ways to service them to minimize the cost. You have to decide, only seeing the request up to time t, what to do to service the tth request. So you have uncertainty about the future, right? if the adversary is mean enough, then it could look at what you're doing. The second you move a server somewhere else, it could come and say, okay, now I want to request there. In fact,
The ball here kicks you to the other side of the field.
yeah. I mean, this model, this is not just a joke. This is one interesting thing is that, for instance, like if you look at poker, especially in Texas Hold'em, poker has converged to people playing these regularized optimal strategies. People talk about their ranges, and they optimize whenever I make a play. Am I betting, like, if I bet a strong hand, that's great, because now I make the pot bigger, I'm likely to win more money. But I also decrease the amount of uncertainty that my player has against me. So now the language of poker is the language of entropy regularized optimization.
Do they know your theorem?
The good players.
Okay. Anyway, it's a good question of whether they internalize the corresponding theorem, and probably the answer is yes, because there's a lot of money involved. Okay, if you set these things up, then there is a k-server conjecture, which is that the competitive ratio for every metric space with more than k points is k. There's a long history of work on this. It was nearly solved by Koutsoupis and Papadimitriou. They gave an upper bound of 2k minus 1. This gap is still open. What's unfortunate about this setup? First of all, k is not a very good bound. It doesn't seem like k. You have k servers, you're paying within a factor k of the optimum, doesn't seem great. Also, the algorithms you get here do not look like the algorithms that people in practice design when they're reasoning under uncertainty, which leads one to believe that maybe there's something slightly wrong with the model, or like maybe it's not capturing what we want. So a very beautiful thing is that if you now just allow your algorithm to be randomized instead of deterministic, it makes random choices, but the adversary cannot see those random choices. Then there is a conjecture. So now you can look at the randomized version. My algorithm still has to act only given things up at the time t, but now I can do something random. Then there is this randomized k-server conjecture that the competitive ratio for every metric space with more than k points is log k. And there is a weak version that was stated at various points in time that it's polylog k. So this weak version is true. There was a lot of work there. This is only some small sampling of it. Let me just say that even some very simple metric spaces, it was very difficult to prove the conjecture. And then in these two works, what do we do? So with Seb, Michael, Yintar, and Oleg, we proved that the competitive ratio is bounded for ultrametrics. So again, for lack of time, an ultrametric is a metric space where the points are the leaves of a tree, and the distance between 2 points is the label assigned to their least common ancestor, and the label should be decreasing along root leaf paths. And in general, I mean, if the labels are decreasing geometrically by some factor, we call this an HST. So here they're decreasing by a factor of 2. We call it a 2 HST. For ultrametrics, we showed that the weak version of the conjecture is true. And then in a follow-up work, I showed that you can randomly approximate your space in a suitable way by ultrametrics so that the ultrametric ideas can be used in general. How does this fit in with the talk? By the way, there's like just so this is what you missed by interrupting. There's a beautiful theory done by a lot of people here 10, 15 years ago about sort of how this relates to metric Ramsey theory, how every metric space contains these hard subspaces. It's really very nice. There's also, it's also known that if you're willing to pay some competitive ratio that depends on the size of the underlying metric space, then ultrametrics are universal. So there's a theorem of Bartol in its optimal form by factor n von Rao and Tawar, which says that you can randomly approximate an n-point metric space up to log n distortion, whatever it means, by a distribution over random ultrametrics. Okay, and then sort of the most recent thing before ours is that for every ultrametric you can get the competitive ratio to be polylog n, where n is the number of points. You combine these two things together, you get something which is polylog n for any metric space. But getting something which is better than k, say even for trees of depth 2, or even when the metric space is the real line, this was open still. So, okay, so we solved those cases. How is it related in 60 seconds to what we talked about now? Good question. So, okay, so first you relax the problem, right? I had a problem that was discrete. It was these configurations of k points in a metric space. Relax it to a fractional version where I just want to maintain a measure of weight k on the metric space. This is nice because now it means I can do things. This gives me an underlying convex body, and it means I can do things in continuous time, which is good for the algorithm I stated before. And then it's a non-trivial fact that without loss you can consider these fractional algorithms. But the point is now that you get some convex body underlying this tree, and then what's the algorithm? So the algorithm is just the one in this setup where the gradient, sort of the vector field is, if a request comes at this leaf, then the vector field is just, you need to move one server here, so the vector field is just pointing in the unit basis direction of this leaf. So now you have a convex body that gives you the vector field. Once you have this regularizer, you get the dynamics. That's the algorithm. What we said, this algorithm would have been discovered long ago, except for the fact is that if you use the natural thing, you have no idea what this means. But it looks like it looks like a weighted entropy. So that suffices for the slide. If you use the natural weighted entropy, it doesn't work because the dynamics get frozen close to the boundary. This is, if you know this area, this is a fundamental difference between competitive analysis and the multi-arm bandit setting. The fact that you're comparing yourself against something that's allowed to switch strategies means that you have to be much more nimble in your algorithm. So the exponential weights, which is what this corresponds to, is not nimble enough. So really the whole difficulty in this area is how do you regularize your regularizer? How do you regularize this phi so that it's nice near the boundary, and making it nice doesn't destroy the other properties of the algorithm. So so there is a way to do it, which depends on the structure of k-server, and that gives a solution. Here's the last. We're done. Here's the last slide. So let me just give you an open problem of Nadi and Joel Friedman, which is a beautiful problem, and somehow it's in this framework, and it's only solved in dimension 2. So here's the problem. You have a sequence of convex bodies that arrive over time, and when the tth convex body arrives at time t, you need to place some point inside the body. Okay? So that's the requirement. What you're trying to minimize is the total movement of your algorithm. So what you pay is the distance you move to get inside the body at time t. And you want to compare this against the best offline algorithm that sees the whole sequence of bodies in advance. Their conjecture is that for every dimension n, you can do it in a way which is competitive, where the competitive ratio depends only on the dimension. In fact, you could conjecture that the competitive ratio should be square root of n. But it's open even in n equals 3 dimensions. They proved it for n equals 2, and it's open even for n equals 3. So let me just, I'm out of time, but let me just tell you, just to give you the flavor of the problem. Suppose your sequence of convex body is a sequence of lines that, say, all intersect in one point. Then the greedy algorithm, say, which moves the minimal distance to get to the next line, you can think about it. If it's out here far from the intersection point, it will move in a circle around the intersection point. Whereas the optimum will say, look, I know what's going to happen here. I'm just going to move to the intersection point and then just stay there forever. So in this case, it's even in their paper, you can get a competitive algorithm by, instead of doing the greedy thing, every time you make some greedy move, you spend a little bit of that movement to move towards the intersection point with the previous line. And really this problem, and the reason this framework is so nice, is to, say, rederive this algorithm in a way that doesn't understand the geometry of intersections of lines. Because that algorithm is very specific to lines. It doesn't work in general. But you could hope that the algorithm can learn about this intersection point without knowing about intersection points. That's a very nice open problem. Let me end with that. Yeah, thanks.